but we have graded homework 2. So you can please feel free to take a look. And if you have any regret requests, then submit on Gradescope. The other announcement is that I'll have the coffee chat instead of the office hours today after the lectures. So you're welcome to stop by if you have availability, but we'll not have any office hours this week. We'll upload the homework 3 later this week, but from next week basically we will be covering material that will be helpful for you to start that homework. It's only 3 problems, so it'll be shorter than homework 2, and then of course homework 4 will be longer, which will be closer to the exam. Okay, so basically the second part, before I go into the details of what we start a new topic, I just want to kind of outline what you can expect to learn in sort of outline of part 2. So remember that in part 1 we started with thinking about defining fluxes, right? So we defined Fourier's law, Fick's law. So here, instead of defining that, we'll define stress. Okay, so stress tensor, we'll define what it is. Then once we have that, we'll have the governing equations of fluid flow. So instead of governing equations of species and mass transport and energy transport, we'll have governing equations of fluid flow. Then we'll have the boundary conditions for fluid flow, how they are different. And finally, first portion of the course will end with fluid statics. That is, you can think of it like a steady state system where we didn't have any complication. We try to make this as easy as possible. In this case, fluid statics means that velocity will be 0. So you still have some properties of stress, but the velocities will be 0. So all of this is chapter 6 of D. So I'd like to go through this outline because I want to show you how the structure that we're developing kind of carries over to part 2, and then it will also carry over to part 3. Okay. So first thing is we define the stress. We have the new governing equations of fluid flow, boundary conditions, fluid statics. Then once we have learned this, we'll start with simplest kind of flows, which are called unidirectional flow. So think of this as the 1D problems that we were doing, unidirectional flows. Okay. Then we'll have nearly unidirectional flows. So this is the lubrication approximation, which will cover nearly unidirectional flows. And these are chapter 7 of Dean book. Okay, this will be chapter 7 of Dean book. So we'll start with again first is then unidirectional, nearly unidirectional flows. Then we'll learn details of creeping flows, which are low Reynolds number flows and have very surprising properties. Chapter 8, and then we'll learn about high Reynolds number flows, which are the other extreme in chapter 9. Okay, so this is kind of what you can expect to learn in this part, and I hope you can see the structure coming through. So emphasis again would be on learning what are the governing equations, what are the boundary conditions, and then as we go along in the course, we'll learn about how to simplify those governing equations and boundary conditions for unidirectional flows, nearly unidirectional flows, creeping flows, and high Reynolds number flows. Okay, so that's essentially the whole outline of part 2. Okay, so before I jump into any of the details of the topics, why do we even care about fluid flow? Like, how is it important? And many of you may not be directly using any of these fluid flow concepts, but it's actually quite important, even indirectly, in many of the research areas that you might be interested in. So how does fluid flow impact? Okay, so fundamentally, you can imagine any of the species transporter we were discussing, we always had this term V dot LCI, which we always ignored, right, in the first part of the class. So now as soon as you add flow, clearly that will change. But from a research perspective, this will have implications in microfluidics. So if you're interested in using microfluidic devices for, let's say, any biological application, or you're just using microfluidics for sort of studying interfacial science, colloids, you want to synthesize colloids, you want to move particles, diagnose particles. Microfluidics is basically low Reynolds number fluid mechanics. And we will cover concepts of how things change or what's different. Okay, so microfluidics is very different from large scale fluid mechanics, where we observe things that are largely not similar. So that's one application. I would say if you're designing any of these devices, a lot of times fluid mechanics considerations do come into picture. If you are using any of these, if you're trying to kind of make any emulsions for your interfacial science, so let's say oil water interfaces, or you have like a cell in a medium, there's an interface, there's an exchange of something across the interface, and there is flow in the background. Again, there is sort of a lot of emphasis on what happens around the system using fluid mechanics. If you're not looking into the areas such as usual, bio side or colloidal side, there is also flow electrochemistry. So now this is also becoming a more, I would say, increasingly important topic is flow electrochemistry. So use devices to actually flow some of these things and have a reaction. So flow electrochemistry involves a lot of transport concepts of fluid mechanics. And so you will basically, whatever you will learn here, while not directly applicable, it will be directly applicable to some of the concepts in flow electrochemistry. All right. Then you have polymers. So polymers are, this is the topic we will not cover in detail, but we mostly focus on idealized fluids. But polymers have non-Newtonian properties. They have flow properties which are very different than usual systems. So understanding how some of these things will change for polymers can be very helpful. Polymers, a characteristic of polymers is their flow properties. And finally, broadly, soft materials. Soft materials are somewhere between a solid and a liquid. We're focusing essentially on the flow properties of a liquid in this part, but soft materials are somewhere in the middle. So, learning these basics will help you kind of go into more advanced topics in soft materials if you're looking to characterize them. So, for instance, some of you may be doing rheology of the systems to characterize your system, or some of you might be measuring some strength of a material, and so you kind of have some of these flow principles also. So, fluid mechanics as a subject is old. But a lot of the applications which are new are very modern, and I've often seen now that I've been here for a few years, is that I see students kind of like coming back to fluid mechanics, designing an experimental setup or analyzing their system. So some of the basics here are actually very relevant to what you will do. Okay, and another just quick sort of like, this is mostly for just interest. Basically, I thought about some interesting kind of concepts of fluid mechanics being applied to different problems. And this is sort of like just 3 examples. Okay, so there's not exhaustive. There's a lot of cool science that happens in fluid mechanics. Just 3 examples I cherry picked, this slide, because I found them to be creative. So what you see here is Professor Pico Hosel from MIT. She's really like a leader in thinking about this sort of fluid mechanics in hairy hydrodynamics. So she calls it hairy hydrodynamics. Basically, it was inspired from sort of organisms, which basically will have hair over their body. But then when you flow something on top of it, because of the presence of this hair, you will have different flow patterns. Okay, so we will cover this in class, and you might have seen this in the undergrad. A simple fluid flow where basically they're shearing something. But what they did experimentally is they added this layer of hair on experimentally also using a soft material, and they showed that everything changes. Very interesting things happen in the system, and so basically how this additional structure modifies what's being found. And so they were able to kind of and you're welcome to read the article which I've cited here. It's kind of, I think, more like a perspective. And the idea is all the classical problem of fluid mechanics can now change. Will change if you add this sort of structure. So this helped them, I think, understand. Forget the animal they were studying, basically how that animal actually drinks water, using sort of this hair as a way to kind of pull the water out. And it was a very interesting set of experiments. I think I may actually have it in the next slide. Yes. So you can see that this is what they created, like created here a material, and they kind of looked how the water kind of goes up, and the properties of this material, the strength of this material actually can help understand that. So again, this is a basic hydrodynamics, but very different angle to it. And so a lot of very interesting mods. So whatever we study actually kind of is very easily applied to what they're doing, just a slight modification. Okay? Another interesting fact, like this is more, curiosity-driven science, I would say, application-driven science, electrochemical systems. So personally, also my group actually is interested in this area. So this is Professor Vinaj from Cornell. Professor Archer has a wide range of interests, including material synthesis, but kind of fluid transport is also one of them within these electrochemical devices. So what you see here are the governing ingredients. Okay, so we will not go into all of these in the class, but I just want to show you that even advanced modeling of electrochemical systems, essentially it boils down to transport equations. So you write transport equations, you write boundary conditions, and that is a difficult part, and then you solve them using sort of an advanced algorithm. But really setting up the problem is where the key is, and this is just one example of how. And I believe this was a non-equivalent fluid example, if I'm not wrong. So they kind of showed how these different patterns change inside the system. Okay. Finally, another fundamental example is Professor Lisa Fauci from Tulane. This is biological hydrodynamics. And what I showed here was sort of something happening within a fluid flow. Here's slightly sort of structural kind of changing the fluid a little bit, but here it's even more coupled. So what you will see here is basically motion changing, sort of creating these patterns behind, and sort of like it's sort of a two-way coupling, right? That those patterns influence it. So there's an elasticity. The material is kind of also changing its shape, right? So these are much more complex, but we will not be able to discuss these things in detail. But I just want to show you that some of the concepts that we learn in the class can actually be extended into very recent topics in research. All right. So this was kind of just like a brief introduction. There is obviously also very classical applications of fluid mechanics, which we'll discuss as we go along in the course. But don't forget that a lot of concepts you have learned here can actually be applied if you're kind of even toying around with some sort of a fluidic device and a setup. Okay. Any questions on these sort of this introduction of part 2 and any structure of part 2? Anything that comes to mind you want to discuss before we go into the topics? All right. Okay. So let's begin. So we'll start with what is stress and how to think about sort of a tensor form of stress and so on. So so let's start. Okay. So let me make it slightly. All right. So first thing is, remember that in part 1 of the course, you were finding concentration, temperature, right? Now you want to find velocity. So you want to find velocity. Ultimate goal is to evaluate velocity, mass average velocity, v vector. Now the thing is, velocity is a vector quantity, right? Velocity is a vector quantity, and that's why it's different in comparison to what we were doing before, because before we were finding one value, concentration, or maybe multiple species, but the equations were sort of like concentration of A, B, or C, or temperature. Now here we have velocity, which is a vector to begin with, right? So that's the key difference, is that as soon as we start talking about velocity, we are trying to now evaluate 3 values all at once, right? Vx, Vy, and Vz, because that is basically what will give us the information. And so to do that, we define something called as a stress tensor, sigma. And let me write this out. Sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yc. So this is sort of a tensor form, and a lot of times the first thing I think students get confused on, and I also get confused on sometimes, and it's not always easy and natural to think, why do we even need a tensor, right? Why do I like, yes, please. Yeah.
Should the second one not be X, not YZ? Second to the left.
Oh, Y, sorry, thanks. Yeah, absolutely. Sorry, that's correct. Yes, YX. Thank you. Yeah. So the first thing I think, and this is very common, right? And like I said, I also many times get confused. Why do I need 9 components to begin with, or if there's symmetric 6 component, but why do I need like a tensor? Sorry. All right. So why do I need even a tensor to begin with? And the answer really comes from the fact that velocity is a vector quantity. We want to find a vector. And so when we think about something which is tensorial, you have to think about that there are components which they have two directions, right? So there is an x direction here, and there are two directions in each element. Right, so two directions in each element here. So let's take an example of this particular sigma yx, okay? And it's very crucial to understand that why there are two directions, okay? So what sigma really has units of force per unit area. Okay, so we have units of force per unit area. Now, when we are thinking of stress, there is clearly, we have said it's units of force per unit area or Newton per meter square. Okay, so if you like to think in terms of dimensions, it's Newton per meter square. So there is an area element. So if there is an area element, there is a plane, because you're thinking of something per unit area, right? So per unit area, you need a surface. You need something which has an area like surface of this sheet. So when you have a surface of this sheet, remember, whenever we define a surface, we need a normal vector, right? So we have a normal vector, which is, so this direction is the direction of the normal. Direction of the normal. And why do I need the second direction? Any thoughts? So I have a surface, and I'm saying sigma is kind of like a force per unit area. And so if I have a surface, I have a direction of the surface, which is direction of the normal to the surface. Why do you think I need the other direction? Right. So the direction in which the force is applied, because force itself also has a direction. Okay. So you need two directions, one to define direction of force. Direction of force, and the other is to define the direction of the surface. And that's the key element. Remember that this is sort of analogous to when we were thinking about fluxes, right? We said fluxes are always normal to the surface, right? We basically said, when you're thinking about fluxes, you think of flux normal to the surface. Here, force doesn't have to be that. Force can also be applied, if I'm thinking of this, force can also be applied parallel or perpendicular, or in plane, it can have any combination. So you need two directions. One is the direction of the surface, and one is the direction of the force. That's why you have this tensorial representation. Okay. But so now let's say, what if I have a surface with a normal n, right? So what if I have a surface? So let's imagine I have a surface here. Let's say a surface here. And I have this sort of fluid somewhere here. And this normal is defined like this. Okay? This is essentially how we have defined the system. How would I think about force applied on the surface? So that is known as a stress vector. S. Stress vector. Okay. And what is a stress vector? It is, so sigma is not force. So it's very common, I would say, in undergrad maybe, or in common terminology, a lot of students think of stress as force per unit area. Note, it's a tensor. Okay, it's a tensor. It's not a vector, so it's not force, right? It is physically, you can try to kind of have the same units, but whenever you're thinking of stress, I want you to think of a tensor. Okay, now whenever you're thinking of a force, you should think of a stress vector. Okay, so that's the key differentiation. If you remember, the stress vector is really force per unit area, and I want to be more specific, force applied, force by the fluid. Okay, so force by the fluid on the plane, by the fluid, and N needs to point into the fluid, applying the force. Okay. So basically, N first stress vector is the force by the fluid on the plane. So whenever you're thinking of force, think of stress vector. Okay. And what is the relationship between stress vector and tensor? We get n dot sigma. So let's say, share this out. This n dot sigma is the definition of stress vector. Okay. So it is basically you take the normal into the fluid, which is applying the force. You calculate the force by the fluid on the plane, and you do an n dot sigma. Now, I hope you can remember this, that when you are thinking of flux through a plane, you were doing n dot q, right? So remember, it's very similar. When we wanted to calculate a flux through a plane, we said it's n dot q, and we knew the direction has to be normal to the surface. Now we are saying we don't know the direction. That will come out by doing this n dot sigma, and we'll get sort of a force vector outside. So a force, if you're thinking of force, immediately you should come into mind stress vector, which is n dot sigma. So it depends on the tensor, but it is not the tensor. It's very important to understand. The tensor is a collection of these 9 quantities. And now when I want to think about force, I want to think of stress vector, which is n dot sigma. Okay. Any first, and I will elaborate this. This is a very key concept. Yes, please. Yeah, I'm just coming to that in a second. Yeah. The question is, what is the difference between a matrix and tensor? I'll come to that in a second. But let's just quickly first also think about these elements. Okay, so we have these 9 elements: direction of the normal to the surface and direction of the force. So let's take some quick poll, and this is just so that you can sort of think about some of these concepts. Let me just turn on the polling. All right, so let's start this. Hopefully this will work. Right. So yeah, so I've sketched a red arrow on top, and hopefully it should come up in a second. All right, yeah, so it will, the poll should be on, it should be on your screens. We have essentially an arrow on the top, and I wanted to think about what do you think the right form is: sigma xy, sigma yy, sigma yx. And let's do like a minute or so on this, and think about how we can, which components, so there are 9 components you said. Okay? So which component do you think is characterized with the red arrow? Let's give another 15 seconds, then we'll wrap up the poll. All right, I'll put in the poll now. I want to get the answers in. All right, so let's see. So great. So almost all of you got it right. It is sigma yx, and let's discuss why it is sigma yx. So this is essentially if I have if I have a system like this. This is y, this is x, and this is z, and I have an arrow like here. Then the surface it was being applied to was ey, right? So sigma, this has to be y, and the direction of the force was an x. This was the direction of the force. Okay, so that was the idea. So it was essentially sigma yx, which is good. So great. So now let's do another one. This is not again that difficult. I just want you to kind of continue to think in terms of the sigma x and y. Let's do another one, which is this one. And let's do a quick poll. This should not take more than 40 seconds. So what is the red arrow which is being shown here? Which component is this? Right, almost everybody has responded. So maybe 5 more seconds so that everybody can respond. All right, post the poll now. All right, so let's take a look. Great. So, correct. So basically, you can think of this in a way that the surface, normal to the surface is x, right? So the first component maybe has to be x, and the direction is z, so it's b, which is sigma cx. Sorry, xc. Okay, great. So let's now carry forward the discussion, which was the question that Tim had asked about how do we think of a matrix and a tensor and so on. All right. So this is B. I just write this for completeness. B is sigma. Let's see. All right. So how do we think about how do I think about this value n dot sigma and even this in terms of vector or a tensor? Okay. So it's up to you. Some of the students do prefer to use sort of a notational index and like, you know, to evaluate vectors and tensors. And I'm actually, I prefer to sometimes just go to using matrix operations because I just find them to be easier. But you can use either or, and we will not be doing too many of these in the class. You'll just do it in a one or two homework problems. That's all. But you should know, if you have a system, how to evaluate these quantities. Okay. In most of the quantities, it becomes much easier for us. But let's say we want to evaluate this whole number n dot sigma, and we have been given sigmas like this. So how do I think about this? So first thing is, I have a dot product of a vector with a tensor. So it's rank 1 versus rank 2, or and so you will basically dot and you come with like get a vector outside. So s dot n, you can think of it also as nx, ny, and z. So this is my n, and this is what I think Tim was asking. This is my n vector. And I am representing it like a row vector, and then I'm representing the tensor as a matrix. Right? So we have this and n, and this is sigma, and this is a 1 cross 3, right? This is 1 row 3 columns, and this is 3 cross 3. So whenever you're doing a matrix multiplication, these two have to be equal, right? And the output will also be 1 cross 3, which is the row vector, which means it will read the vector. Okay, so 1 cross 3 times 3 cross 3. So you can think of it like a matrix multiplication. Okay? Some students are just, for them it's easier to use if they use before an index notation, they kind of just sum it out automatically. But if you prefer it, and actually I use this all the time, I go and write it like this, and definitely also it's the same thing essentially. So how will I calculate something like this? Is matrix multiplication, and basically you take this, you multiply individually. So you multiply this with this, ny with this, nz with this, and then you sum them, right? And that becomes the first element. You do the second, and then you do the first. So that's how we do it. So let's do this for a simple case. Okay, I don't want you to do it for a full general case. I will let you do this. I'll give you 2 minutes or so. Let's do for a simple case here. Why don't you do find Sn when n is equal to ey? Okay, so just you multiply this, do a matrix multiplication, and I'll give you a couple of minutes. Take your time, and we'll discuss this how to think of this when we have n equal to ey. What do you think will come out to be? And then we'll try to specifically understand. And yeah, feel free to talk to each other, or just to get the answer and work together if you want to clarify. Yeah, but this is, so that would. Yeah.
Yeah.
All right, almost all of you have gotten your answers in, but you are welcome to post them for another few seconds, and then we'll take a look and do it together. All right. So let's take a look. So it's some of you have said A, some of you have said B, most of you have said C. The correct answer is C. So one of the things I want to emphasize here is how can I, even without looking at the full, we will do the math, okay? But I want to emphasize something which is very important here, is that we want to find force on something which is normal to EY, okay? Normal to EY, which components of stress will have normal to EY, which are the first subscript as Y, right? So they will, obviously the first subscript of this is, you can do the math, but I also want you to, when you get the answer, you can check. It physically makes sense that the first subscript here are Y, because my SN is EY, right? So if my SN is EY, I should expect the components which are normal to Y to come up, which do come up. I'll come to in 1 second. And then the direction is multiplied with the direction. All right, this one. Yeah, great question. So this is absolutely the main points I want to really emphasize. It is just the surface which is normal to EY, but the force on that surface can have 3 components. So think of it like this. This is my surface, right? My normal is EY, okay? Now it doesn't mean that the force applied on the surface will only be in EY or EX or EZ. It can be in all 3. And that would be determined by my stress tensor. It may be so that my sigma YY is 0. It may be so my sigma Y is 0. It may be all of 3 of them are 0. But that stress in these 3 components together in 3 different directions will multiply the 3 different directions will tell me what the effective force is. Because the key component is that normal just tells you that that's a direction of the surface, but the direction of the force can be independent of that. Like it will be dependent on the values of sigma Y, sigma. So it doesn't mean that the force will be on the plane outside the plane. It can be at an angle to the plane, right? Because it depends on the 3 components. So it's very critical to understand. Let's imagine if sigma YY is 0. Okay, so there is no component which is perpendicular to the plane. It's all on the plane. But maybe the other 2 components are 0 and only sigma YY, in which case the forces is perpendicular. So that is the key component of understanding that the stress tensor is required to get in 2 directions. One is the direction of the force, which is this one, and one is the direction of the normal, so which is EY. Okay, so let's do this in once, like in the calculations ourselves, just to kind of show you if you're not as familiar with this math, is that you individually multiply these components. So it was 0, 1, 0 is EY. So you multiply each component and then you sum them. So it's 0 times sigma XX plus 1 times sigma YX plus 0 times sigma ZX. So it is sigma YX. My first component, then it's sigma YY in my second component, and sigma YZ is my third component. So we'll kind of repeat this cycle with each row, with each column, and this means it's sigma YX EX, Y plus sigma YZ EC. Okay. All right, where do you think the complication will start to happen? So we get this answer, this really makes sense. This is when the normal is no longer something as simple as EY. When the normal is curved, then your normal can sometimes be dependent, will be changing, and then you'll have all these sort of combinations coming through of the stress tensors to kind of get the force and final stress. Okay, so I think this is a good time to, let me just check. Yes, this is a good time to take a break. So let's return at 12:47, and what we'll do is we'll take this value of stress and then stress tensor and understanding of stress vector, and then we'll start to go towards calculating the loading equation. We'll end the task. Right, take 5 minutes and then we'll discuss. Sure.
I started reading,
Right.
and then I realized that I was taking the point all game volumetric, but then that shows up again wherever she plays, have data is not even. So we want.
Oh, no, not again. Yeah, if the approach for the second part is correct.
Yeah, so yeah, that's what I was. So I'm gonna change my.
Sure.
Not that like 50% doesn't matter. It doesn't matter.
That's
Yes.
so that's very common, and that at the end of the day, you want to like keep the keep the error to 2 hours. Yeah, correct. Absolutely.
Word reasoning says that I don't know if that's just because.
So yeah, so basically the one I might have started. But we are not going to be as long as we're mostly international. It's a more of a like it's an experience. Yeah. Yeah, absolutely. So technical concepts
I think it's beginning.
probably, but the first lecture I know, fine, but it should be as so my guess is two of them were do it. One was the so that I might have restarted. So yes, don't worry about it.
And then with that,
Yeah.
I can't take it.
Yeah.
So I figured out. And I tried to figure out. My last time I might
See, I think really one so it's just kind of like
I'm just gonna get as well. Yeah, move that as well. So I actually figured it out. I didn't expect to. We'll reach out. I gotta figure out.
Sure, yeah, I mean, like I said, I'm flexible. I'm happy to work with you. Like I said, just let me know what works best for you. Once you can see the only sometimes the only challenge is that I'm generally pretty smart in setting exam, but sometimes it's fine evenings. So that's the only thing. But 7 Sunday. And 8 I want to get it should be fine.
I think I'm gonna take my time. I don't know. It's could keep us this fly back.
All right, so let's get started. It's 12:47. So now the next goal for the class is to derive a governing equation for fluid flow. Governing equation for fluid flow. All right. And I should note that the book has a much more general derivation and I've just found it to be difficult to kind of sometimes follow. So I will do a much more simple derivation in the class. That's not part of the book. But just to let you know, this is, and just a reminder, this is chapter 6 in the Dean's book. So I'll be doing a slightly different derivation just because I find this to be simpler and more instructive at times. The book has a much more general vector derivation. So, all right, we'll go back to the control volume. So again, we saw the stress tensor similar to and the stress vector, and now we're thinking about forces on a balance for fluid flow on a control volume. All right. So control volume, remember, this is very similar to what we did in part 1, delta x, delta y, delta z. All right. And as you saw in one of the exam problems, we gave you in minus out plus generated is equal to accumulated. That was the idea of, what is the steady state and so on. That was for a conservation or a heat, right? A scalar has the value of in minus out plus generated is equal to accumulated. In this is now we will do a momentum balance. So this is very important. We'll do a momentum balance. A momentum balance. And for that, the equation is rate of change of momentum. Rate of change of momentum plus momentum outflow. Okay. Momentum outflow is equal to the net force applied. Okay, is equal to force. It was very important. Do you remember this sort of physical sort of like you may have heard this? Where have you heard this sort of relationship? Where have you heard this? Which law? Newton's law, right? Rate of change of momentum is force applied. Right? That is equal to ma or mdv by dt. But here there is another term. This is momentum outflow. That is not typically seen in the usual when you think of rate of change of momentum. And why do we have that? Is because remember we're thinking of control volume, and now we are thinking of things going in and out. When we talk about a rate of change of momentum equal to force, in usual Newton's law, we think of a rigid body. Now we are doing a balance in a fluid flow, where something can go in and go out. Okay, so that's why there's a correction there. There are again more mathematical details. You can go into kind of this defines the left hand side as a rate of change of momentum with sort of a time derivative, but we will not go there. But the whole point is the slight difference is because there's a fluid flow. Okay? So rate of change of momentum plus momentum outflow is equal to force. Now this is note that momentum is what m times v. So it's mass times velocity is momentum. I don't want to kind of write the terms like in one side. So I'll say there are 4 terms that we focus on, 1, 2, and force has 2 parts. And what are the 2 parts? Is the force on something like control volume like this can be volumetric. It can be on inside like the entire volume. That is, let's say 4 volumetric force, or it can be surface force. So it can be a volumetric force, it can be a surface force, it's still a force. Right? So what are the surface forces? Those are what we were discussing, stresses, right, per unit area. What is an example of a volumetric force? Gravity, right? It goes everywhere. It doesn't matter which part of the volume you experience gravity, right? So volumetric forces like gravity and surface forces, which is like stresses. So that's sort of the way to think about these 2 things. So rate of change of momentum plus momentum outflow is equal to force, just 2 parts, surface force and volume. So any questions on this sort of text equation? Anything that's confusing here? Make sense? All right. All right. So what is the how should I think about this? Is that momentum is mass times velocity. So if I want to write the balance, I'm actually writing a balance on a vector. And obviously writing a balance on a vector is writing a balance on 3 components. So out of simplicity, we will only write component on 1 component, and then we'll say we'll generalize it to 3 components. Okay. So just want to clarify step by step. This is an equation. So this is not with what we did in the species and heat equation. It was just a scalar. So we just had 1 balance. Now we have 3 balances implicit, and because of 3 directions. Okay. So basically let's go there. So we'll focus on the Vx direction. So balance in the x direction. So let's say balance in x direction. Balance in x direction. Right? So balance in x direction. And now we have rate of change of momentum. So what is momentum? Momentum is mass times velocity. And we are thinking in terms of volume. So we'll think of density times volume as mass. So it's del by del T. So this is first term, del by del T of rho Vx, delta x, delta y, delta z. Okay. Rho Vx. So this is, think of this as mass times Vx. Okay. Where m is equal to rho times delta x, delta y. The rate of change of momentum. Change in momentum with respect to time. Okay, so this is my first term. The second term is where things start to become more complicated. Okay, so we have first is this is rate of change of momentum. So we wrote the momentum in the x direction. So let me just further clarify momentum in x direction. So rate of change of momentum in x direction. Now you have to think about momentum outflow. So let's think of like it's like this. I'm sketching this again, control volume. So could anybody kind of physically, if you have not seen this before, especially, could you physically tell me what do you think is momentum outflow or inflow? What does it mean? Momentum outflow. What would it physically mean? Absolutely. So basically physically it means some sort of momentum is leaving the surfaces, right? First part that. So we have 6 surfaces, right? 6 surfaces, so something leaving the surface is the outflow. So inflow is that's minus of outflow, right? Inflow and outflow. Now let's focus on this surface. This surface. So first is momentum outflow will be through the surfaces. So let's just write it. Momentum outflow will be through the surfaces. Through the surfaces. So great answer, because you can think it's kind of a surface. So it's coming. So we are not thinking of a volume now, we're thinking of a surface. So how do I even think about that in terms of like it's momentum, so it's mass times velocity. So how can I like it's outflow? So like what do you think is one way to approach it? Like what do you think could be one way to get to that number of like momentum outflow? Any thoughts? Like we want to think of momentum outflow in the x direction through the surface. Any thoughts? Like, yeah.
Like by diffusion and fraction of momentum.
So good track. So what Colin is saying is should be through diffusion momentum of convection. Remember that when we are thinking of total mass, there is no diffusion. Okay, so we remember that rho, when we think of rho, there is no sort of diffusion of like just in terms of momentum outflow. Okay? So there is no sort of like, so it's purely convection, but point well taken. It could be some sort of a transfer, right? So the idea is that I know the velocity has to be Vx, right? Because that's the direction I'm interested in. But the mass coming in, which is the mass and velocity, depends on the surface I have. So the mass coming into that surface would be, how can I calculate the mass coming through that surface? But in time, that's rho Vx. This is, and it will become a little bit clearer. And let's look at the units of this is kg per meter cube, meter per second, meter square. So this is kg per second. Okay, so there's mass coming in. Sorry. So sorry, yes, yeah, delta by delta z. Delta by delta z. This is mass coming in per second multiplied with Vx. Okay, so this is the idea that momentum outflow, there is some mass coming in, and I can find the mass by taking the component of the velocity, Vx, but this is coming in, this is not going out, because the direction of the x is coming in. So this is minus rho Vx, delta y, delta z at x. Okay. The other side, I will have, if velocity is in the Vx direction, I will have mass going out. So that's the outflow. So that will be plus rho Vx, delta y delta z x plus delta x. All right. Now this is the first part, and sometimes this is, it looks, once you see it looks okay, that makes sense. And I think this is the second part is where more confusion starts to happen. And let's think of this two surfaces, the green ones, okay, and the green ones. So now when I'm thinking of that surface, remember we are still doing a balance in the x direction, okay? So our mass and velocity is always in the x direction. So how can I find the mass through these surfaces? Any idea? And this is the confusing part. So remember, the mass will only come through the velocity in the y direction. That's the mass. That's not so the and then convected in the x direction. So the mass comes across the surface. So I take the normal component. So in the bottom part, I'll say minus rho vy delta x delta z. This is my mass coming into that surface, but it is getting convected in the x direction because I'm doing a balance in the x direction. Okay, y plus rho vy vx delta x delta z. And similarly, I will have rho vz vx delta x delta y at z plus rho vz vx by z plus delta z. Any questions on these terms? Because the most confusing element sometimes becomes, why do I have two velocities? So I would say first velocity is the mass coming to that surface. The second velocity is the direction of the moment. So note that this is Vy and it's multiplied with x and z because it's the mass coming in and then times the mass. Any questions on this momentum outflow term? All good? Any? Okay. I think everybody is comfortable with this, and the units can sometimes help. 50 kg per second times velocity. That's rate of change of same units, rate of change of momentum. All right. Okay. So let's keep going. So we have two terms now. So we have done the rate of change of momentum, which was a volumetric term, then the momentum outflow, which was a surface term. Now we have forces, which have now two terms. So third is the forces. Okay, so this is the surface forces. All right, so this is, again, let's sketch our control volume. All right, the control volume. Now, surface forces, I obviously need to go one force by one force. First question for all of you. In Newton's law, is it forces by the body or on the body? It's important, right? Now we are thinking of forces. So is it force by the body or on the body? Because we are thinking of forces. So forces we need to think of, is the force being applied to or applied by the body? So forces on the body, right? So we're thinking of now forces on this control volume. Okay, the forces on this control volume. Now, this is very important, is when I think of forces on a surface, I think of stress vector. Okay, so don't forget that. Stress vector is very important. So when I'm thinking of the forces, I'm thinking of the stress vector. All right. Now, but in this problem, I'm also focusing on the stress vector in the x direction, because we are only focusing on the x direction balance. Okay. So when I'm thinking of forces, surface forces, think stress vector, but we are only interested in the x direction. X direction. All right. Okay, so that's the first thing, and I elaborate in what I mean by that. So let's start with the first test case. Let's say this is my surface, and let me just say x, y, z again. X, y, and z. The green surface. Now I want to find the force on the green surface. So which way might be my normal point? How can I find my normal point? Minus x. So Tim says minus x. Tim, what? Why do you think it's minus ex? Yes. So how? Yeah. So I mean, I'm very. So I want to see. I want you to kind of think about stress vector. So we're thinking of stress vector. What is the stress vector? Stress vector is the force applied by the fluid, right? Force applied by the fluid. So which fluid? And I want to look into force on the fluid, right? I'm looking at force on the fluid. So how can I find force on this green surface? If I'm looking in this direction, then the fluid that will be applying the force is outside, right? Remember our definition. This is if n points into the fluid, that is the force applied by that yellow fluid in that sort of region. Here, now my normal, if I point it into minus ex, that will be the force which will be applied by some fluid outside here, right? And the force applied by the fluid outside will be the force on the green surface. So that is the description. If you use that for normal, that is fine. If what Ian said that you take the normal inside, then you have to do a minus of that force because that is the force by the fluid. So you can use either or, the answer will come out to be the same. So the main point is that it should either be a stress vector of minus Ex or minus of stress vector of Ex, both work, but it has to be either gives. So this is negative of force negative of the force by the fluid and this is literally just force on the fluid. So it's the same and they're both equal. So you can use either or, just you have to be careful of the sign. Okay, you can use minus Ex or you can use minus of S of Ex, but the idea should be the same because it's negative of the force by the fluid inside or fluid inside. Any questions here? Does that clarify the idea? So you take it outside because that's the force by the outside fluid, so it will be on the inside fluid, or you take it inside, but then said I'll reverse it to get the full force on the fluid. Okay. So on this surface, basically, I will say I have the force S of minus Ex times delta Y delta Z. Okay. Is that all I'll take? Is that what I'm looking for right now? What I'm actually calling so this is true that this is the force, but we are doing the balance in the x direction. So I'll find this value and I take the x component. Okay, because I'm doing the balance. So this is correct, this is the force on that surface, but I'm not doing the balance of the full force, I'm only doing the balance of the x. Okay. So you are welcome to do this, but it's not very difficult to see. I'll just show you that we have done it for EY and we got this, right? So we got 3 components. So you will get, like, if I'm taking the x component only, it will be just this, right? So similarly, you start to see only tensor like 1 components coming in. So let's just, I'll just write it down and it will become clear. And this will come out and this started with Ex because I'm only doing a balance in the x direction. Only x direction balance. And so this will come out to be minus sigma xx times delta y delta z at x minus delta y delta z. Okay. So that will be the component that will come on this surface. So the normal is x, and I'm only interested in the x. So normal is x, and I'm only interested in the x component. So both the directions are always interested. Yes. Yeah, yes, absolutely. So yeah, if you're doing the full problem, yes, absolutely, absolutely. So we'll get an answer at the end, but we are kind of simplifying that by only focusing on next question. Absolutely. So we get this value and note the negative sign comes because of the normal relation. Yes, no. So that's just to get the net force instead of this force per unit area. So stress vector is force per unit area, right? So you want to get the force in that force, the balance that you're doing. So that's why we're multiplying with the areas and everything to get the dimensional matching. All right. Okay. So this is clearly. So just to kind of maybe this part is this. I hope you can see that the other side now my normal will be plus Ex because I'll point into the fluid outside that goes on the fluid. So it becomes plus sigma XX, sigma XX plus delta X, delta Y, delta Z. So this part here. And then finally, I will similarly start to get minus sigma YX at Y delta X delta Z plus sigma YX at Y plus delta Y delta X delta Z. Then I will get minus sigma ZX times at Z delta X delta Y plus sigma ZX Z plus delta Z delta X delta Y. Okay. So note that all the components have the second part as X, which makes sense because I'm only looking at the X direction balance right now. The first direction is changing because I'm looking at all the 6 surfaces, that's 6 components, and the normal is changing from X to Y to Z. Okay. And the negative sign is coming because of the direction of the normals. I hope this is clear. Any questions? Yes. So can you repeat the question? In specific cases? Oh no, so yeah, so good question. So what Noah is asking, if I understand correctly, is saying, well, you're only looking at the force in the X direction. So shouldn't these some of these terms go to 0 because they have this Y and Z? The answer is not necessarily, right? Because we are focusing on the force in the X direction. That's why the second subscript is X, right? The first subscript can be X, Y, or Z because that's just the direction of the plane. Okay, so the direction of the plane can be arbitrary. It doesn't have to be just X. It can be arbitrary. The direction of the second component has to be X, or the second subscript has to be X because we are only doing a balancing. So no, it doesn't have to necessarily go to 0 because we are doing a balancing expression. Yes, please. Yeah, very good. So what you're asking a question for that. Actually, more suitable for the next lecture, but what I'm saying is, well, this looks more like I'm pushing the surface because my force is the same as the normal one, and the other ones are more like shear forces, which are basically scraping along the surfaces, and that is absolutely. And we'll discuss that a little bit more in the next class. Any other questions? A good question. Any other questions here? All right. Okay. So we get this, and then finally, the fourth term is force, which is volumetric. I will, for the simplicity, I will only focus on the gravity force because it's just the easiest. You can have other volumetric forces. So can anybody suggest any other volumetric force, which depends on the volume? Magnetic force, electric force, and so on. So we'll discuss the electric force way more in the last couple of lectures in the course, just to get an idea of how to think about electrochemical systems and so on. But basically, it doesn't have to be just gravity. Okay. For now, we'll be So buoyancy, that is actually the homework problem. So basically, that's a great question. So buoyancy, as we will discuss, is actually not a volumetric force. Buoyancy happens because of pressure forces. So we'll discuss that in a bit more detail. A good question, and we'll discuss that in higher time. Any other questions? Yeah, good question. So magnetic electric forces are basically can be thought of as volumetric because they depend on the charge, net charge, on the volume. But for now, for simplicity, we just focus on the mass, which is the gravity. Okay, so this gravity force is simply rho gx times delta x delta y delta c. And what is gx is just the component of the gravity in the x direction. Okay. All right, so sum, and I'll skip a few steps, just, sum 1, 2, 3, and 4, and divide by the volume to make it a per unit volume equation. Divide by delta x, delta y, delta z, and what you get is rho del vx by del t plus del by del x of rho vxx plus del by del y of rho vx vy plus del by del z of rho vx vz is equal to del by del x of sigma xx, del by del y of sigma yx, z of sigma cx plus rho gx. This is system number 1, system number 2, system number 3, system number. Okay, so we get this expression, and don't worry about some of the details. It's easy to see. Just a matter of doing some of these derivatives. But this is a full equation you will get once you have done all the balances, and you get our data. So first term is the rate of change in momentum. Second term is which has 3 terms, which is the momentum also. The third term again it has 3 terms, is the surface forces, and the fourth term is the volume. So this is our Newton's second law kind of sort of balance for a fluid in a volume per unit volume basis. Okay. Any questions at this point before I simplify it further? Okay. So some of you could see, and this is just sort of like you can see that there is something hidden inside this expression, and that's the continuity equation. Okay. So look at this. So there's a Vx here, there is a Vx here, there is a Vx here, and there is a Vx here. If I take that Vx out somehow, then I'll get a del rho by del t plus del by del x of rho Vx plus del by rho y of del Vy plus del by del z of rho Vz, right? And that's your continuity equation. And that is precisely what you can do by using a product rule. Is you can write it like this. And we know that this is equal to 0 because of conservation of mass. And then plus, you will get rho of del Vx by del t plus rho plus Vx del Vx by del x plus Vy del Vx by del y plus Vz del Vx by del z. And then these two terms remain the same. Okay? So same terms. So the idea being that basically you can simply kind of combine the first and second term and sort of get simplification. You can sort of simplify it like this, so that the density comes outside, inside the derivative inside. This makes the life a little bit easier this way. So finally, this is equal to this plus this is your equation. And when you generalize in 3 dimensions, and as Julie was pointing out, you will start to get tensors back. It becomes V dot del V is equal to del dot sigma is rho g. So this is the governing equation that you can derive finally after doing all the calculations. So this equation essentially is the principal equation that allows you to have the yes.
Is that function, does it equal to 0?
Yes, correct. This is 0 because of continuity. So remember, continuity is del rho by del t plus del dot rho v, right? Is equal to 0, and that's the continuity, exactly continuity equation inside. So that's why this is the continuity equation. Any questions here in the derivation? Yes, please. Oh yeah, that's interesting. So what the question is does the rho gx need to be there because gravity will only be in one direction? That's a great question. So the reason it prototypes is sometimes the coordinate system is not as defined as that the gravity will always be in the z direction. You may be building your coordinate system to that side there, but you're absolutely right. Gravity will be in one direction. If my coordinate system is generally the usual one, x, y, and z. But I may be kind of rotating my coordinate system in that case. Kind of, that's the only. So yeah, so that depends again on this cylinder. So whether it's in the coordinate.
I guess it's like the radial.
Right. Align. So yeah, you have to then take the components. One part in radial, one part in theta. Yeah, that's where you basically start to put. So what we're saying is, if my z is just an r and theta like this, how do I do it? And so basically, what you do is then you go with the book, there's an appendix, and tell you how to transform from one coordinate to another. And we will do some of these examples, maybe not necessarily for gravity, but we will do some examples of how to transform from a Cartesian to a cylindrical, from a Cartesian to a spherical, spherical to a Cartesian. That's actually required because forces cannot be integrated by Cartesian coordinates. For forces to integrate, you have to come back to EX, EY, and EZ. So we'll discuss some of the separateness. We'll come to that absolutely. There is another question? Yes. Correct. Yeah, so basically what is this V dot del? So this V dot del is kind of sometimes known as an operator. Basically, this is Vx del by del x. This Vy del by del y. This Vz del by del z, and it's being operated on a velocity, which has kind of so it's like an operator. Think of it like this, like an operator which is being applied on some sort of a vector. So it takes a little bit getting used to, but you'll see it in time. Three parts. Right? That's how. So it could be like a divergence or something. That's when you get a vector. And our gradient is only on scale. So to just summarize, today we have discussed what is a stress tensor, what is a stress vector, and then we have derived this equation. On Monday, what we'll start to do is we'll start to kind of look into boundary conditions, and we'll start to see how to come together with this governing equation, and we'll also discuss how to break this stress tensor sigma. So just like flux, right? We broke it down into different parts. We break down the stress into a pressure part and a shear stress part, as was asked before about the normal and shear components. And then we'll derive the same Navier-Stokes equation, and then we'll look at the boundary conditions, and after that we'll start to solve. Okay. So yeah, that's it for today. And then yeah, if anybody's interested, I'll be here for just to chat for another hour. Yeah, so that's it. And then we'll see you all on Monday. And we'll upload the homework 3 in a couple of days.